Download this code from codegive.com, link in the description below. OK, let's dive into the build heap algorithm, its time complexity proof, and a code example. This is a fundamental concept in understanding heaps and priority queues. What is a heap? A heap is a specialized tree-based data structure that satisfies the heap property. There are two main types of heaps. Min heap for every node I in the heap, the key value of I is less than or equal to the keys of its children. The smallest element is at the root. Max heap for every node I in the heap, the key value of I is greater than or equal to the keys of its children. The largest element is at the root. Heaps are typically implemented as complete binary trees, which means all levels are completely filled, except possibly the last level, which is filled from left to right. This allows efficient storage in an array. Why build a heap? The build heap algorithm is used to convert an arbitrary array into a valid heap. This is a crucial step in heap-based algorithms like heap sort sorting algorithm that leverages the heap data structure. Priority queues data structures that efficiently manage a set of elements based on priority. Graph algorithms, example Dijkstra's algorithm used for finding shortest paths, where the priority queue is implemented with a heap. The build heap algorithm. The build heap algorithm typically involves the following steps. 1. Start from the middle, non-leaf, nodes begin from the first non-leaf node, which is at index n/2, 1 in a zero-indexed array of size n. Why this index? Because nodes from index n/2 to n1 are the leaf nodes in the complete binary tree representation. 2. Heapify, sift down for each node from the first non-leaf node back to the root, index 0, call the heapify, also known as sift down or max heapify/min heapify, function. The heapify function ensures that the subtree rooted at the current node satisfies the heap property. 3. Iterate * repeat the heapify process for all non-leaf nodes, moving towards the root. The heapify function, sift down. The heapify function is the core of the build heap algorithm. It takes a node index as input and recursively ensures that the subtree rooted at that index satisfies the heap property. Here's how it works, for a max heap example. 1. Find largest child * find the largest element among the node itself and its children. 2. Swap, if necessary if the largest element is not the node itself, swap the node with the largest child. 3. Recursive call * recursively call heapify on the subtree rooted at the child that was swapped. This ensures that the heap property is maintained down the tree. Pseudocode for build heap. Code example, Python. Time complexity analysis, O(n). The crucial part is understanding why the build heap algorithm has a time complexity of O(n), even though it seems like it involves nested loops, a loop from n/2, 1 to 0 and a recursive heapify function. The naive argument is this: we loop n/2 times, and each heapify could take O log n time, the height of the tree. This seems like O(n) log n. However, a more careful analysis reveals O(n). Here's the detailed breakdown. 1. Heights of nodes *. The key is to realize that not all calls to heapify take O log n time. The time complexity of heapify depends on the height of the node at which it's called. The higher the node in the tree, the lower its height and the faster heapify will execute. 2. Number of nodes at each height *. Let h be the height of the heap. The root node is at height h, and the leaves are at height 0. In a complete binary tree, there are at most n/2 h plus 1 nodes of height h. Asterisk the time complexity of calling heapify on a node of height h is O, h. 3. Total time complexity asterisk to calculate the total time complexity of the build heap algorithm, we need to sum the time complexity of heapify for all nodes. For evaluating the sum asterisk the summation from h equals 0 to h equals log 2n of h/2 caret h plus 1 converges to a constant value less than 2. You can demonstrate this using calculus or by recognizing it as a geometric-like series. In essence, the higher the node, the fewer nodes there are, and the less significant its contribution to the overall complexity. 5. Final result asterisk since the summation converges to a constant, the total time complexity becomes O, n asterisk constant, equals O, n. Mathematical proof, sketch. Let's denote the height of the heap by h equals floor, log 2n. The time complexity is dominated by the sum, where c is a constant factor. We need to show that sum, h equals 0 to h/2 caret, h plus 1, is bounded by a constant. Let's consider the infinite sum. To evaluate this, we can use a trick. The right side is a geometric series that converges to 1. Therefore, the infinite sum is 1, and the original sum, h equals 0 to h/2 caret, h plus 1, is bounded by 1. Thus, t, n, equals c asterisk n asterisk 1 equals O, n. In summary, asterisk the build heap algorithm transforms an arbitrary array into a heap. Asterisk it iterates from the first non-leaf node to the root, calling heapify on each node. Asterisk while heapify has a worst-case time complexity of O, log n, the overall time complexity of build heap is O, n, because the heights of the nodes being heapified are taken into account, and the sum of those heights, weighted by the number of nodes at that height, converges to a constant. Asterisk the O, n, time complexity makes build heap a very efficient way to initialize a heap. Let me know if you'd like a more rigorous mathematical proof or further clarification on any of these concepts.